No. The other three. It is hard to start. Minimize minus but हमारी आवाज चल रही है माइक्रोफोन चल रहा है all right so welcome everybody to the fall physics colloquium series. We have an excellent speaker with us here today who happens to be a former student, and it's always a pleasure to actually interact with him. And I'm fairly certain that today is not going to be any different either. He's going to be talking about testing ER not equal to EPR. And well, okay, go ahead. Go ahead, Irfan.
Hey everyone, thank you for being here for my talk. Today I'm going to be talking about testing ER equals EPR, but as you might guess from the title slide, I'm going to be talking about something actually somewhat different. So this is a project that I did with a professor from my group, Professor Edward Wilson Ewing, and it's not related to what I did during my PhD. That work was in a different area of quantum gravity, that's semi-classical gravity. This is related to what's known as tabletop tests of quantum gravity, but it's also close to my heart because I think it involves some real physics where you actually get to test your predictions against data that you get from a lab. So let me, before diving into the main content, I'll give you a brief timeline or history of this project. So our particle accelerators currently give us an accurate picture of physics up to energy scales of about 10 tera-electron volts, but not more than that. Maybe we could extrapolate another order of magnitude, but not beyond that. But it's generally expected that quantum gravity effects would become significant on energy scales of the order of 10 to the 16 tera-electron volts. Clearly, which is the Planck energy, clearly we are orders of magnitude away from that, from achieving those scales. They're clearly out of reach. So what we do is we try to get experimental constraints on quantum gravity from what are known as tabletop tests. As the name implies, these are experiments that you can do in a lab on the top of a table that is on everyday energy scales, which are much more approachable. And this is what this project began as. Our purpose was to propose experimental tests to test this important conjecture in quantum gravity that I'm going to expand on during the course of the talk, known as ER equals EPR. And we did propose some experiments, not just one, but two. Then, fortunately or unfortunately, my supervisor happened. I would keep discussing my side projects with him, that, oh, I'm working on this too, I'm working on that too. And I happened to discuss this project with him as well. And he just hated ER equals EPR, just with religion, period. He just hated the idea. He didn't like this proposal. And therefore, he would put really incisive questions to me. Why does this make sense? Why does that make sense? Why this and why not that? And in that grilling, he came up with something so fundamental that I could not answer it. And he then suggested that I apply all the knowledge I gleaned from the experimental proposals that I'd made and apply it to the most well-known bipartite or system of two particles in physics, which is the hydrogen atom. One electron, one proton. I know I'm talking about just one isotope, but for the purposes of this talk, hydrogen means one electron and one proton. It's the most well-studied system. It's the system that we have the most precise data on. And as I set out to test the predictions of ER equals EPR in the context of hydrogen, I saw them fail miserably one by one. And therefore, I was forced to turn this project from one that tested for ER equals EPR, from one that suggested experiments for ER equals EPR to one that discredited the proposal. And I'm going to dive into the main content. And let's begin. Oh, here's him, by the way. Seems very happy with what he did to my project. So in quantum gravity, our research in quantum gravity has shown us that entanglement, quantum entanglement, is connected with the idea of space-time connectivity. And by the latter, I mean that space, the connected piece that you can go from one point to another. There are no gaps, there are no holes, and so on and so forth. So the two ideas seem very connected. There are strong hints from quantum gravity from all areas, all sub-areas of quantum gravity, that the two concepts are deeply connected with each other. So much so that it suggested that entanglement might even generate connectivity, that the two can't exist, that the two are basically the same. Examples of this include the famous ADS-CFT proposal, where connectivity in asymptotically anti-de Sitter space is related to quantum entanglement in quantum field theory, or a very specific kind of quantum field theory known as conformal field theory. Similarly, in loop quantum gravity, when you have to connect space slices, what you do is that you entangle degrees of freedom on them. Those degrees of freedom correspond to the quantum geometry on our spatial slices, and so on and so forth. A stronger conjecture along these lines was put forth in 2013 by Maldacen and Susskind. This is one Maldacen and Leonard Susskind. It's their proposal, the stronger conjecture, which is known as ER equals EPR. What they said was that any two particles, two molecules, two electrons, there could be any two particles, not just quantum geometry, or their CFT duals for that matter. Any two particles, whenever they're entangled, they're connected by what they call a quantum wormhole. They said it's the quantum counterpart of what we classically know as wormholes. In other words, they said that an Einstein-Rosen bridge, or ER bridge, or wormholes, as they are called today, always accompany Einstein-Podolsky-Rosen or EPR pairs, or entangled particles. And this tells you why this proposal is called ER equals EPR. It tells that wormholes in geometry, on the geometry side, are equal to entanglement on the quantum side. So you generate entanglement between two particles, they're going to be connected in space by a wormhole. Now, the main question we want to be addressing is, since systems of two particles or bipartite systems, entangled two particles or bipartite entangled systems, as they're known in physics, are accessible at lab scales. Today, we work with multipartite systems. They're very accessible. We can control the entanglement properties, quantum control them. This is all being done at on laboratory scales. Since they are so accessible at lab scales, could we use them to test ER equals EPR? Because the proposal is about them. And what we're going to show is that with well-studied bipartite systems and reasonable assumptions, the answer is and for the purposes of this talk, the particular bipartite entangled systems that I'm going to focus on are systems of charged particles. Because one of the effects of ER equals EPR, we can guess, is going to be on the electric field surrounding the two particles. Because if you change the geometry of your space, by geometry here, I mean specifically topology, you have, say, a two-dimensional piece of paper. You introduce on it what's known as a topological handle. You introduce on it a pipe. It's going to change the topology of this space. And if electric field lines remain in this space, it's going to change how they flow through the space, right? So one of the effects of ER equals EPR is going to be on the electric field surrounding the particles. So the electrostatic interaction is going to change. And in our analysis, we're going to allow both possibilities of non-traversable and traversable wormholes. By the latter, traversable, I mean wormholes which allow electric field to enter one of the mouths. This is one of the mouths of the wormhole. They allow the electric field to travel all the way through the throat of the wormhole. This tube is known as the throat. And they allow the electric field to come out through the other mouth. And we're also going to allow the possibility of non-traversable wormholes. Electric fields also leak into non-traversable wormholes, but they can't make it through the throat and out of the other mouth. We're going to consider both these possibilities in our analysis. And before we could make some concrete calculations, we have to make some assumptions. And the reason for this is the original ER equals EPR paper, and this is one of the reasons my advisor hated that proposal. It's a 50-page paper, and this is what it stops at. It just says that any two entangled particles are connected by a quantum wormhole. It doesn't do any calculations. This is what the proposal is. It doesn't go on to define what quantum wormholes mean. So we have to, in order to do some calculations, we have to make some assumptions about what we mean by a quantum wormhole and what do quantum wormholes mean for our calculations. The first of our assumptions is, and they are reasonable assumptions extracted from what that proposal means. We assume that quantum wormholes always link the entangled degrees of freedom. For instance, if the degrees of freedom entangled are the centers of masses of the two particles, and the quantum wormhole is going to have its mouths really close to the centers of masses of the two particles. And for concreteness, I assume that the wormhole mouth is going to be about a distance of alpha times Planck length away from the degree of freedom entangled. And alpha here is a constant of order unity. This is the first of our assumptions. The second of our assumptions is that the wormhole mouths always remain close to these degrees of freedom entangled. For instance, if this degree of freedom or the particle, I'm going to use the word particle as of now, it seems to, if it happens to be moving, and the wormhole mouth would move with it at the same velocity so that it remains close to this degree of freedom. Or if this degree of freedom happens to exist in spatial superposition of positions, then so is the wormhole mouth. It's going to be in the same spatial superposition. For instance, if I have two electrons, they're entangled, they're spin half systems, I can entangle them using the spins, and I put one of the electrons away. Then if I pass the other electron through, say, a Stern-Gerlach apparatus that puts it into a spatial superposition of positions, then I'm going to have my wormhole, the second wormhole mouth is going to be in the same superposition, spatial superposition of positions, so that it's always close. It's always close to the degree of freedom entanglement. The third of our assumptions is because these are quantum wormholes, we expect that their properties, their geometrical properties, will be described by operators. We assume that there's a self-adjoint operator, A hat, corresponding to the area of the wormhole throat. And this comes from a proposal about black holes, about black hole entropy, that the expectation value of A is given by, could be estimated by this quantity, where LP/L squared is the Planck length squared, gives you the Planck area, and A could be estimated by this quantity. S here is the entanglement entropy. It describes the quantity of entanglement between the two particles that are entangled. This is the third of our assumptions. The fourth of our assumptions is, I know it's becoming a lot of assumptions, but this is what we have to do to make concrete calculations, because as I said, the original proposal was really ambiguous. The electron is a point particle. We're going to see that in order for ER equals EPR effects to be significant, we need to work with point particles. And an electron is going to be one of the particles that we work with. It appears in the hydrogen atom. We assume that the electron is a point particle. It's a reasonable assumption because from theories, we don't have any reason to expect that there's a substructure to the electron as there is to the proton. And experiments to date have established only an upper bound on the size of an electron, which is 10 to the negative 20 meters. We know that we are still far from the Planck scale, but we can make this assumption because we don't have any other reason to suppose a substructure to an electron. Just to give you an example, if the particles that are entangled are really big, their charges are distributed all over their volume, and the wormhole mouth is at the center of mass, then very little flux is going to leak into the wormhole mouth. In order for ER equals EPR effects to be significant, we want to be working with point particles or particles that have an extent at most that of a Planck length or Planck volume. And the final of our assumptions is that the electric fields actually leak into the quantum wormholes that we have. They can travel, they can move through traversable wormholes or just simply leak into the non-traversable wormholes. And we need to make this assumption. It's a technical point, because if you start entangling two particles and ER equals EPR says that a wormhole appears as the particles are entangled, you're looking at a continuous topology change of your space. And if you had electric field lines spread into your space already, then a continuous topology change would refer to a breaking of electric field of the electric field lines. The electric field lines would have to break to leak into the wormhole, and that can't happen classically. we assume that that can happen quantum mechanically because the original configuration could tunnel into a new configuration where the electric field leaks into the wormhole, and we assume that there is a non-zero probability of that happening. The probability is not so low that it takes so long as to be greater than the age of the universe for the system to tunnel into this configuration where the electric field leaks into the quantum wormhole. So we assume that this is possible.
Excuse me, what do you mean by electric field has to break?
Oh, the electric field lines. So suppose that I have a two-dimensional surface and there's this topological handle on that surface. And it is introduced as a continuous topology change from the first plane surface to this second surface. Then the electric field lines from one particle, if they start going into the wormhole, they can't go into the wormhole without breaking. If they have to come out again and go out to infinity, the line would have to break. And this can't happen with Faraday flux lines classically. So if there's a continuous topology change to classical geometry, then the flux through this wormhole is going to be zero, because the electric field line would go in, but ultimately would have to come out, because if it has to leak into the wormhole and go out to infinity, then it would have to break. And that can't happen classically. So therefore, we focus on quantum wormholes, and we assume that the system can tunnel into a configuration where the electric field is leaking into our quantum wormhole.
Okay.
And we assume that the flux through this topological handle is such that it minimizes the energy of our, I don't know how I said that.
White wormholes are disabled.
We're still gonna have online meetings. I'll find a way to fix this thing.
Okay.
We're gonna have online meetings. Yeah, this is somebody loves you like like crazy.
Amar is there.
Can you just
I'm not doing that.
You were my top candidate for loving Irfan, yeah.
नहीं वो और बात है.
It's the whiteboard.
Whiteboard.
Can you just yeah, I think this will probably fix things.
Yeah, so back to the point I was making, we assume that the flux through these wormholes is such as to minimize the energy of this electric field configuration. That's somewhat intuitive, because this wormhole provides you with extra space, provides the electric field with an extra space to expand.
Can the wormholes have some kind of a vacuum polarization or something like that?
They can. That's a very important question. I'd come to that.
Okay.
So what's going to happen is we assume that the flux through the wormholes is such as to minimize the energy, because the wormholes provide you electric field some space to expand into. So the energy to begin with goes down as the electric field lines gradually tunnel into this configuration where they're flowing through the wormhole. And but if you concentrate all the electric field lines into the wormhole, the energy is again going to go up. So there's this Goldilocks minimum region where the energy of the configuration is going to be minimized, and that we assume that is what the system ultimately tunnels into. And that's the final of our assumptions. And with the assumptions out of the way, I'm going to move on to their consequences. Okay, so consider two particles which are entangled and which have charges Q sub A and Q sub B. Assume that particle B is really far from A, so its electric field does not directly affect the electric field surrounding the particle A. Now, because they're entangled, let's focus on particle A. Because they're entangled, there's supposed to be a wormhole mouth close to particle A. Here it is. And we assume that we are working with non-traversable wormholes to begin with, just for the sake of simplicity. Now, you'd see our assumptions coming in one by one. This wormhole mouth is a distance of alpha times Planck length away from our particle. Let's draw a sphere called S sub delta of the same radius about particle A. Now, the import of doing so is that the magnitude of the electric field at every point on this sphere is going to be the same as the magnitude of the electric field at every point on this wormhole mouth. Okay, and I can use this fact in conjunction with Gauss' law to calculate the magnitude of this electric. Now, Gauss' law tells us that the total flux, electric flux coming out of particle A, which is this Q sub A over epsilon 0, is given by the magnitude of the electric field, which is the same everywhere on the sphere S delta and everywhere on the wormhole mouth, times the total area that this electric field goes through, which is the area of the sphere, which is 4 pi times its radius squared, plus the area of the wormhole mouth, which is 4SLPL squared. This is coming from one of our assumptions. And using this,
you're assuming that the two particles are in flat spacetime
yes.
and that the wormhole doesn't have any, it doesn't distort the spacetime.
Yes, yes. So this is all happening at lab scales. So you don't have, significant curvatures. You can assume that everything is in flat space here.
But also the wormhole is not affecting the background spacetime.
Yes. Yeah. So the only feature that we're using is that the wormhole has some area that the electric field can go through. That's all. So we have these two areas, they're multiplying the electric field magnitude, and using this, I can calculate the electric field magnitude like so. Now, if I draw another sphere, concentric with S sub delta, but which has a radius much bigger than alpha times Planck length, then I know that the flux that's coming through this sphere, S delta, is going to be the same that the flux that goes through the sphere S. Okay, I can equate these two fluxes to calculate the electric field at every point on this bigger sphere S. So you equate the fluxes, and this gives you the electric field at this bigger sphere, which I call E sub S. Okay. Looking at this, I can see that's the usual electric field modulated by this extra special factor, which is a factor that depends on the entanglement entropy between particles A and B. It's an important factor because I'm going to call it the special factor because it's going to show up again and again during the course of this talk.
How do you know that the wormhole retains the spherical symmetry of the electric field?
Because the wormhole is really small. It's of Planck.
So it doesn't disturb the electric field distribution.
Yeah, So here, I mean, really close here, the electric field would not be exactly spherically symmetric. We'll be making this approximation. So once you're really far away from the this Planck distance, then everything is nearly spherically symmetric.
Then it's fine. Yeah.
So you can see that this formula, you can do a rereading of this formula where you have that the electric field from particle A is the usual electric field, except that it's coming from a charge that has been reduced by a factor of 1 plus S over pi alpha squared. So it's just this charge inserted into the usual electric field formula. And this actually makes it easier for us to discuss these things, these processes, because we can speak in terms of fractions of charges that are lost through the wormhole or that travel through the wormhole to appear at the position of the other charge, because this is precisely what the electric field lines represent in this case as our calculations show. For instance, if I'm dealing with traversable wormholes, then the electric field from particle A is given by this usual factor times the total charge that's sitting at the position of particle A, which is a fractional charge that's left with particle A, plus the fractional charge lost by particle B, which appeared at the position of particle A. Remember that particle B was really far from particle A, so it can't directly affect the electric field around particle A, but it can affect the electric field around particle A by losing some of its fractional charge through the wormhole, which appears at the position of particle A. And concretely, the fractional charge left at particle A is this, is the original charge modulated by the special factor, plus the charge lost by particle B, which is the original charge of particle B minus the charge that's left with particle. So is this mechanics all clear? I'm going to pause here for a few minutes if there are any questions, because now I'm going to move into the applications of these rules to the hydrogen atom.
Can you just recall where this factor of S, which is the measure of
The entanglement.
from an assumption?
Yeah, that's from an assumption. That's from the assumption that the wormhole area is given by this 4s Planck length square. This is from the black hole entropy formula. So we assuming that that holds at the microscopic level as well, because that's the only proposal that we have.
So that includes the measure of
Yes.
Entropy.
So if entropy is 0, if the two particles are not entangled, it means that the wormhole area is 0. So there's basically no wormhole connecting the two particles. Yeah. So that's from one of the assumptions. Yeah.
So higher the degree of entanglement, larger will this factor be.
Yes.
So isn't this a very wild assumption, or
It is a very valid assumption, and therefore we are looking at its consequences in the context of the hydrogen atom.
Do we need to assume that these are point charges?
What?
You mentioned one of the assumptions that you're dealing with point charges. Right?
So the assumption is that the electron is a point charge. The proton could have a size, because we don't have any, reason to assume that it's not.
No, that will probably come in later when you do hydrogen, right?
Yes.
Over
yes,
here,
yes.
Q and QB, you haven't really.
They are point charges. I'm assuming they're point. Any other questions?
So far, what you've done, you just need to assume that they're spherically symmetric.
Yes. That's actually not I mean, you could call an assumption, but it's coming
No.
from.
I mean, if it's point, then it's obviously spherically symmetric. All I'm saying is that so far what you've done, to me, it sounds that might as well give them some extent, whatever extent, but as long as
Yes,
it's spherically,
yes.
I think that's the
That's
point.
exactly what it is.
I think that's the point that Adam
Yes,
is
yes,
trying
yes.
to make.
Yeah.
And so far, the only thing that you've said is basically, the only thing that you've used is spherical symmetry.
Yes. Yeah. Basically.
Okay.
Any other questions?
This might be a stupid, naive question, but
Okay.
once you have introduced this non-traversable wormhole,
Yeah.
you're adding the two areas, right? The first thing, right?
Yes.
If the wormhole comes in, I mean, maybe the first term reduces as well in your area. 4 pi alpha square LPL square.
So here, no, it doesn't reduce. So the wormhole is in addition to this area of the sphere.
Right.
So they're always going to add. It's always going to provide you with some extra area for the electric field to leak into.
Okay, so that's your assumption,
Yeah,
right? Okay,
yeah.
so
So it's not,
something like
it's not
it's not
displacing.
taking the place. Yeah, that's
Exactly. Yeah. Good question. So should I move on? Okay. So yeah.
So I guess the idea is that somehow there's an extra dimension in which the
Yes,
is leaking in.
precisely. And that's why the electric field reduces, and that's why we can speak of the charges getting lost somehow.
Mhm.
So coming to the hydrogen atom, we, as I mentioned before as well, hydrogen atom is the most well-studied bipartite system in physics. Its spectrum is known accurately to 12 decimal places. That's, I guess, the as precise as we've been able to get so far with our theories. Now, if a proton and electron in the hydrogen atom are connected by a non-traversable wormhole, for now, let's consider non-traversable wormholes again for the sake of simplicity, then the charge of the electron, as per the rules I've introduced, gets reduced by this factor. So the charge of the electron becomes negative E prime, which is equal to negative E. Negative E is the original charge of the electron divided by a special factor. The charge of the proton has E because the proton is huge in comparison with Planck area, and doesn't. It's assuming that its charge is distributed all over its volume. It loses only negligible flux through that wormhole. So the charge of electrons, a proton stays E, whereas the charge of the electron goes down by this factor. Now the spectrum of hydrogen is given by this formula. So I've substituted the charge of the electron, I've substituted the charge of the proton, and this gives me a modified spectrum, which is modified by two factors, two inverse powers of our special factor. And just to give you, if alpha equals 1, remember that alpha was supposed to be a constant of order unity. Maximum entanglement between electron and the proton, they're both spin 1/2 systems, so we can entangle them maximally through their spins, and the maximal entanglement corresponds to an entanglement entropy of log 2. It gives the 2 powers of this factor a value 1.49, and this corresponds to a 33% increase in all the energies, which is a huge increase given that those energies are known correct to 12 decimal places. Even if alpha is as big as 5, it's supposed to be a constant of order unity. If it's too big, we won't consider wormholes to be really connecting the degrees of freedom. Even if it's as big as 5, or even, I mean, if you take it to 10, you get significant changes. S equals log 2 results in a value of this for 2 powers of this vector, which is a 1.7% increase. Again, a huge increase. To be more explicit, this is the picture of the spectrum that you get. A 33% increase would mean that the ground state energy of the hydrogen goes up from negative 13.6 electron volts to negative 9.13 electron volts.
Sorry for interruption. इसमें मुझे जो key ingredient नजर आ रहा है ये है somehow एक जो measure of entanglement है उसको convert किया है into a measure.
Yes.
And then essentially everything else is just calculations.
जी.
तो उसकी आप कोई logic provide करेंगे कि कैसे उस जो measure है उसको, because I would imagine there might be other ways of converting it to area. So
Yes.
that's what's the key here, especially in terms of the number.
What we're doing here is merely looking at the consequences of a proposal.
वो तो ठीक है,
जी.
लेकिन इस particular proposal के अंदर आपने जैसे जो entanglement है, let's say you say if it is they're maximally entangled, then you know S is log 2, and then it in proportion to the pi alpha square, that it's coming out as a number, and that's what is giving us all the changes.
Yes.
अगर उसी को मैं measure of entanglement को किसी और area से scale कर लूं, I can bring it down to almost any number that I want.
So you're saying कि आप entanglement entropy की जगह negativity इस्तेमाल कर लें?
Just let's say I say कि जो area wormhole का it will correspond to, it's like some constant time s, and then I can take that constant anything.
0.1 times the length
हाँ,
का,
तो आपने
0.01 times the length
Yeah, so मैं वही कह रहा हूँ कि मुख्तलिफ entanglement measures की values मुख्तलिफ हो सकती हैं. जैसे negativity एक measure है, उसकी value maximum entanglement के log नहीं
आपके
होगी.
लिए क्या reason है, आपने कैसे इसको ये choose किया?
Why can't I
Okay.
choose S equals some constant times the length too?
So ये वाला, so this comes from one of our assumptions, this one, that the expectation value of the area is given by this. This is coming from the black hole entropy formula, which says that the area corresponding to entanglement, the entropy corresponding to entanglement is given by this area over 4 times the Newton's constant. This is a proposal for black hole entropy coming from Hawking.
वो जो black hole वाला expression है उसको आप यहाँ पे use
जी, हम assume करें कि वो microscopic level पे भी hold करता है.
even if there's no black hole.
Even if there's no black hole, क्योंकि वो वाला जो proposal है, it
So that's like the fundamental assumption.
Yeah. वो वाला जो hold करता है वो सिर्फ black holes के लिए hold करता है. आप show कर सकते हैं वो किसी भी किस्म के horizon के लिए hold करता है. Even in Rindler space जिसमें आपके पास वो Rindler horizons आते हैं, उनके लिए भी वो proposal hold करता है. और isolated horizons के लिए भी वही वाला proposal hold करता है. It's a very general proposal. और हम ये assume करें कि it holds all the way down to black hole.
That's it's a semi-classical calculation.
It's a semi-classical calculation.
But this, what you're doing here is fully quantum.
No, it's not fully quantum because we're doing it at lab scales. You would be doing fully quantum calculations in the context of quantum gravity if you're working in really high curvatures, like the beginning of the universe or the center of the black hole. Here, we're treating the electric field as a classical paradigm.
Quantum सिर्फ आपकी आ रही है S के through, जिसमें आप entropy.
Yes.
Everything else is
exactly. So we are dealing with tabletop tests here. Your tabletop tests, they are all, we can assume that that's.
क्योंकि उससे वो जो आपकी number change आ रही है, it's too big and.
Yeah. I mean, proposal is so we at its consequences, it's applied to the hydrogen atom.
what does it physically mean to have the electron spin?
इलेक्ट्रॉन एंटेंगल प्रोटॉन के साथ
हाँ,
ये कह रहे हैं कि अगर एंटेंगल करते हैं हाइड्रोजन में इलेक्ट्रॉन को प्रोटॉन के साथ, फिर ये एनर्जी लेवल शिफ्ट आएंगे। लेकिन ये तो द एनर्जी लेवल फॉर्मूला यू हैव यूज्ड इज द मोस्ट क्रूड वन, राइट? इसमें आपने कोई भी फाइन स्ट्रक्चर हाइलाइट ऑन हाइपर फाइन, तो दूर के पास लैम्प
इलेक्ट्रॉन ही एक है, वो होगा ही नहीं।
लेकिन ये ज्यादा बड़ी कॉन्ट्रीब्यूशन है।
हाँ, मैं राग हो रहा हूँ, ऐसा कैसे?
उनसे प्रॉब्लम होती है। तो फिर आप वो
कंट्रीब्यूशन
क्यों नहीं लेते, डाइहाइड्रोजन मॉलिक्यूल क्यों नहीं लेते इसके अंदर 2 इलेक्ट्रॉन्स हैं?
सर इसको किसी भी चीज के लिए टेस्ट किया जा सकता है।
उसमें तो वाकई अब एंटेंगलमेंट, वो जो अगर आप सिग्मा बॉन्ड देखें उसके अंदर तो वाकई स्पिन्स एंटेंगल इलेक्ट्रॉन। पहला सवाल तो ये है कि इलेक्ट्रॉन प्रोटॉन को एंटेंगल कैसे करेंगे वो?
सर जी सर, इट्स अ वेरी इंपॉर्टेंट क्वेश्चन। इससे पहली बात तो ये, इसको आप हाइड्रोफाइन कंट्रोल के जरिए एंटेंगल कर सकते हैं। लेकिन दूसरी बात, आई एम जस्ट कमिंग टू दैट, हाइड्रोजन एटम बजाते खुद एक इंट्रिंसिक एंटेंगलमेंट रखता है। जब हम इसकी कैलकुलेशन करते हैं तो जब हम इसके एनर्जी लेवल्स कैलकुलेट करते हैं, वी आर वर्किंग इन अ पर्टिकुलर कोऑर्डिनेट सिस्टम, जिसमें हम सेंटर ऑफ मास कोऑर्डिनेट इस्तेमाल करते हैं, जिसमें हम सेपरेशन वेक्टर कोऑर्डिनेट इस्तेमाल करते हैं। वो जो हमारे यूजुअल एनएलपी वेव फंक्शंस होते हैं, दे आर वेव फंक्शंस ऑफ द सेपरेशन वेक्टर। तो आपके जो हाइड्रोजन एटम का ओवरऑल वेव फंक्शन है, इट्स अ प्रोडक्ट स्टेट। इट्स अ प्रोडक्ट स्टेट ऑफ द स्टेट ऑफ द सेंटर ऑफ मास टाइम्स द स्टेट ऑफ द सेपरेशन वेक्टर। अब वहां पे आर और जो कैपिटल आर है वो अनएंटेंगल्ड डिग्रीज ऑफ फ्रीडम है। बट जब आप इसको वेव फंक्शन को टोटल को लिख लेते हैं एंड यू रीराइट इट इन टर्म्स ऑफ द ओरिजिनल कोऑर्डिनेट्स, जिसमें वो सेंटर ऑफ मास ऑफ द इलेक्ट्रॉन और सेंटर ऑफ मास ऑफ द प्रोटॉन इन्वॉल्व होगा, यू फाइंड दैट द वेव फंक्शन इज एंटेंगल्ड इफ यू कंसीडर दैट सेपरेशन।
यस, कि आप कोऑर्डिनेट फ्रेम्स चेंज अगर कर दें, डिग्री ऑफ एंटेंगलमेंट कैसे चेंज हो?
So this is not changing the coordinate systems. This is like looking at a different separation of the systems. जैसे A, B, C आपके पास systems हों, उसमें आप A और C को आप
So this is
entanglement
changing coordinates, right? I mean, so the concern is that just by changing coordinates, you are saying in one set of coordinates you're saying that it's an entangled state, in another set of coordinates you're saying that the same quantum state is not entangled. That doesn't make sense.
So it's not a change of coordinates.
It is.
Well, you could.
I mean, so I have a quantum state जिसको मैं I am choosing to say that it is in मेरा जो center of mass है वो एक given basically किसी एक state के अंदर है, ठीक है, and with respect to the lab it's at rest. And then I just have my relative coordinate, which, for example, is in the ground state.
Yes.
Now, this is a specific quantum state, and it would have a certain coordinate representation in these coordinates.
Yes.
All that you're doing by going to the other set of coordinates is just a change of basis.
Sir,
I think it might be a change of degrees of freedom.
it's actually a different partitioning of the same degrees of freedom. Different partition. जैसे आप systems लेते हैं ना कि A, B, C, ये तो अब मैं कंटिन्यूअस डिग्रीज ऑफ फ्रीडम की बात कर रहा हूँ, तो यहाँ पे ये थोड़ा सा कंफ्यूजिंग लग रहा है। लेकिन अगर मैं डिस्क्रीट की बात करूँ, जैसे A, B, C मेरे पास या D है, उसे मैं ऐसे कर सकता हूँ, मैं A और B को एक साथ कर दूँ, C और D को एक साथ कर दूँ, एंड आई कैलकुलेट द एंटेंगलमेंट एंट्रोपी फॉर दिस सिस्टम। मुझे पता चलेगा कि AC जो है वो हो सकता है B और
So what I can so to add to this thing, so maybe what you're saying is कि जो ये जिस quantum state का मैं जिक्र कर रहा हूँ, आप उस quantum state का जिक्र नहीं कर रहे। And only then can it be entangled, right? I mean, there's no way.
No, I'm referring to the same. It's the same a quantum state. There's a whole paper on it. It's called intrinsic entanglement of the hydrogen atom. जिसमें वो यही करते हैं कि पहले आप हाइड्रोजन एटम को इस उसके वेव फंक्शन को ऐसे पार्टीशन करते हैं कि you're looking at the wave function that wave function of the center of mass coordinate and the separation vector coordinate, and then you look at the wave function. It's the same state, but you look at the wave function of the center of mass of the electron and the center of mass of the proton, and you can show that the hydrogen atom is entangled in the center of mass of the electron is entangled with the center of mass of the proton, but the center of mass coordinate is not entangled with the separation vector.
These are different degrees of freedom. I think the center of mass of the whole system is not. That's one way of looking at the system. Another is कि ये electron है, ये proton है.
Yeah.
experiment आप करोगे आप electron या proton पे करोगे ना measurement
Yeah,
for example.
lab.
In that sense, then of course, it's not the same thing.
Okay, so I'll have to look at that paper, but I still have my doubts about it.
Okay.
Because it seems to me that you're doing a change of basis.
Sure,
or
sure.
Something fishy is happening. Okay, but
So, that was a very important question. Okay, so yeah, just to be explicit, हमारा जो ground state है, it's going from an energy of -13.6.
so can you say something about the degree of entanglement? Let's say coming from that particular paper, what's the intrinsic degree of entanglement?
Away with the degree of entanglement?
आपने अभी what is the
The
intrinsic entropy of entanglement?
entanglement hydrogen, how big is it?
Hydrogen के अंदर how big
Oh,
is it?
it's of order one, order one,
Okay.
order one. So entanglement entropy is not defined for that system. Entanglement entropy, when you calculate it, it turns out to be infinite. But you can use other measures which turn out to be of order one. And from here, when I say a comparison between different measures of entanglement, I'm using the wormhole area as my guide. So in similar systems, in this system, entanglement entropy is turning out to be infinite, but I can look at two particle systems which have similar interactions, like two oscillators interacting with each other through another harmonic oscillator interaction. In those systems, the entanglement entropy is well defined. It turns out to be of order one. So you say, okay, if the interaction is like this, it's similar to the interaction of the hydrogen atom, the area should be the same here. So यहाँ पे हमारी जो reasonably defined measure of entanglement होगा वो भी of order one. So through area हम उनको connect कर रहे हैं. Should I go on?
Yeah.
So up till now we were looking at non-traversable wormholes. If the wormhole is traversable, on the other hand, the proton behaves as if a charge of this has appeared at its center. Remember that the electron was a point particle, so it's going to lose some of its charge, and the charge that it loses is its original charge minus the charge that it's left with. So a charge of this has appeared at the center of the proton if the wormhole is traversable. And the net charge of the proton then is E double prime, which is the original charge of the proton plus the charge that appears at its center. And this is the new charge of the proton, which is equal to the charge that the electron is left with. There's a typo here. No, there's no typo. So the new charge of the proton is this, which means the charge of the electron stays E prime in the case of non-traversable wormholes because the proton is too big, it can't lose any of its charge that appears at the center of the electron. So the electron charge is still the same modified charge as before. The spectrum of hydrogen then takes this form. Now we have to substitute a modified charge for the proton as well, which means that the new spectrum has 4 inverse powers of our special factor, meaning that all the percentage effects that I calculated earlier would almost double now for all the energies E sub n. For instance, the -13.6 electron volt, which earlier was going up to -9.13 electron volt, is going to go up to -6.13 electron volts. So non-traversable wormholes, they disfavor ER equals EPR even more strongly, or doubly strongly. In the case of non-traversable wormholes, remember that only the electron lost part of its charge. The proton charge remained the same. But this means that the hydrogen atom shouldn't acquire a net charge. So we can use this as a further point to discredit ER equals EPR, because the original proposal involved only non-traversable wormholes. We are considering traversable wormholes as well as an extra point. But the original proposal said that a non-traversable wormhole appears between the two particles. And this means that the net charge of the hydrogen atom is the charge of the proton plus the charge of the electron, which is the modified charge. You get this net charge, which for alpha equals 1 and maximal entanglement is about this, 0.18 times the fundamental electronic charge, and alpha is 5, you get this approximately, but both of these are orders of magnitude away from the maximum charge that has been established on the hydrogen atom through experiments, which is 10 to the -20 times the fundamental electronic charge. It is quite intuitive that if the interaction between the electron and the proton changes, the size of the electron, the average size of the hydrogen atom is going to change. So then the charge of electron has gone down, but the charge of both the electron and the proton have gone down. Their electrostatic interaction is going to decrease, and the average size of the hydrogen atom is going to increase. We can use the Bohr radius to characterize this average size. And in the case of non-traversable wormholes, where only the charge of the electron changes, the Bohr radius goes up by one of these factors. And with traversable wormholes present, the charge of both the electron and the proton changes. So the Bohr radius goes up by 2 powers of this factor. Now, it's very difficult to measure these changes in size of the hydrogen atom directly, but there's an indirect method to measure these changes to see their effects. Could I ask the students here if they have any idea about that? Do you have any indirect method in mind that I could look at to see the effects of these changes in the size of the in the size of the hydrogen atom?
None of us are so.
वो एक पीछे बैठा हुआ है
Any idea? Okay.
So
So,
optical spectroscopy. Optical spectroscopy के जरिए.
Precisely. I
तो
mean,
पीछे जो आपने दिखाया है, पीछे जो रिजल्ट्स दिखाए हैं वो इसी की मरहूने मिन्नत नहीं.
जी सर, लेकिन मैं कह रहा हूँ कि या आई शुड हैव एडेड कि इसके अलावा या
ऑप्टिकल स्पेक्ट्रोस्कोपी तो सबसे ऑब्वियस है.
जी ऑफ कोर्स. मैंने ऊपर ऐसे हिंट दिया, ये क्वेश्चन आप पूछना नहीं चाहिए था. Hyperfine structure. So the hydrogen atom happens to have a fine structure.
In orbit interaction.
Yeah, that's the fine structure, but I'm focusing on the hyperfine structure. So
spin coupling.
Spin coupling, yes. Yes, आप उसको इस तरह से कह सकते हैं. Yes. So the hydrogen atom on top of these energy levels has a fine structure. This is known as the hyperfine. So I'm using the word fine. Yes. So a hyperfine structure. So what does hyperfine structure mean? When the ground state electron, or in any state, I'm just using the ground state for simplicity purposes. When the ground state electron of the hydrogen atom finds itself in the magnetic field of the proton, because it has a spin, it alters the magnetic field. The ground state energy splits, okay? And that split depends on the strength of the magnetic field held by the electron. When the size of the hydrogen atom increases, average size, all the quantities here, averages, this is an entirely quantum mechanical calculation, you can do this. When the size of the hydrogen atom increases, the strength of the magnetic field held by the electron should go down, and therefore the split should go down. And we know that it does because we saw the effects on the Bohr radius of the presence of wormholes. This diagram represents the hyperfine split. The split occurs between 2 kinds of states. One is known as the singlet state of the hydrogen atom, and the other 3 states correspond to the other kind. These are known as the degenerate triplet states of the hydrogen atom. Now you can see that the ground state is the singlet state is already entangled, but only one of the triplet states is entangled. So these are the only states that are going to be affected by the presence of wormholes. Now, what the presence of wormholes does is that it changes the size of the split. The size of the split goes down because the magnetic field felt by the electron goes down due to the change in the size of the atom.
But the other 2 states would still be affected by the spatial entanglement, right?
They should be affected by this.
The spatial entanglement.
Yes, but I haven't mentioned that up to now. Yeah, but they would be affected. Yeah. Actually, yes, they would be affected. We're just looking at entanglement between the spin Hilbert spaces. Yes. So this is the exact formula for the hyperfine split. Now, the only thing that changes in this formula, you might say that the electronic charge here changes, but the charge of the proton that doesn't change. And this is the charge, this vector of charge is coming through the charge that goes into the magnetic field formula. That doesn't change because the spin is not changing. So the magnetic field produced is not going to change. The only factor for simplicity purposes, I'm just going to tell you, you can do this calculation. The only factor in this formula that changes is the Bohr radius. So when we have non-traversable wormholes, the Bohr radius goes up by 1 power of our special factor. So the hyperpoint split comes down by three of its powers. For traversable ones, the Bohr radius goes up by 2 powers of our special factor. So the hyperpoint split comes down by 6 powers of our special factor. Now, the hyperpoint structure, it corresponds to the famous 21 centimeter line. It's known as the hydrogen line. It's the most, one of the most prevalent radiations in the universe. You know, it's like the whole universe. It's screaming at you. It's saying ER is not EPR. So to be explicit, when alpha is 1 and you have maximal entanglement, this gets pushed to the 21 centimeter line gets pushed to 38.2 centimeter line. And for in the non-traversable case, but when you have traversable wormholes, it gets pushed to a whopping 69.5 centimeter line. So this also discredits the ER equals.
But in reality, you won't just have 38.2 or 69.
Exactly.
Because you can have intermediate
Yes, yes.
species of entanglement as well.
Yeah.
You basically anywhere between.
No, actually, not here, because the hyperpoint split occurs between fully entangled states.
Right.
Yeah.
Okay.
And we've never seen these lines, so we can conclude that well, ER is not EPR. Now, there's another important point. There are other possible transitions as well, because a transition could occur from, say, this state to this state. So here, I mean, looking at this diagram, we see that the ER equals EPR imposes a split, and an additional split on the hyperpoint structure, a split that's never observed. So that's a further point that we can use to discredit ER equals EPR, because we never see the splitting of the hyperpoint structure. And here comes that point about intrinsic entanglement. When we solve the hydrogen atom eigenvalue or spectrum problem, we work in these coordinates. We calculate the center of mass coordinate for the hydrogen atom. We calculate the separation vector coordinate for the hydrogen atom, and the eigenstates of the hydrogen atom product states. They're the usual NLM states. These are states of the separation vector, and we have the state for the center of mass. This is the usual wave function for the hydrogen atom. It's a product state. But if you now replace R by its expression, capital R by its expression, and you try to calculate the density matrix, and then you find you calculate the partial trace of the density matrix to find the density matrix either for the electron coordinate or for the proton coordinate, you find that the density matrix is mixed. So the electron coordinate is entangled in the same state. The electron coordinate is entangled with the proton coordinate, and this is known as the intrinsic entanglement of the hydrogen atom. It's like always there, and whereas, as I mentioned before, you cannot calculate the entanglement entropy in this case because that is undefined for the system as it is for almost any quantum field theory. It turns out to be infinite. You can look at entanglement entropy in similar systems. One of those similar systems that I did calculations for is a system of 2 harmonic oscillators interacting with each other through another harmonic oscillator interaction. It's like 2 masses on a spring interacting through another spring. You find that entanglement entropy or any other reasonable measure of entropy that could be used in this case is of order unity. And if you use unity for S, which is not entanglement entropy now, with alpha equals 1 and alpha equals 5, you find these values for this special factor. And these values are almost the same as the values we calculated with spin entanglement. So even in the absence of spin entanglement, you should be able to observe all the changes that you've seen before. So what we have seen is that if our assumptions are true, then high precision data on hydrogen suggests that ER might not be EPR. What we have not seen is that you can do further tests which involve special kinds of atoms known as Rydberg atoms. Now, what's a Rydberg atom? You can turn any atom into a Rydberg atom. You just put the outermost electron into a really high n state, and that outer electron then sees only the charge of only 1 proton because the inner electrons shield the nucleus, and the net charge is that of 1 proton. If the outer electron is far enough, it sees only 1 proton. So the outer electron behaves as if it's in the high end state of a hydrogen atom. You can use these atoms to do further tests that further discredit ER equals EPR, and those tests involve the calculations of intrinsic entanglement. Why they're easy? For Rydberg atoms, because in Rydberg atoms, the outermost electron is highly confined about a certain radius. So it behaves as if it's a classical electron. Its wave function is highly confined, and the radius it's confined about is n squared, and is the principal quantum number times the Bohr radius. So you can use these atoms to do these further tests. I've just left them out for brevity purposes. And
the hyperfine splitting would be more complicated, right?
yes, it will
Because
be.
you also have to take into account that the proton is going around the electron, and then you have to take the orbital motion of the proton into account as well. Here you didn't, because it was an S state, right?
But I think that's for the fine structure.
No, even for the hyperfine. you
Yeah, for the
take it.
hyperfine structure, okay. Sure.
So, by the way, in any experimental studies, have there been any observed difference between the spectra of unentangled and entangled hydrogen atoms?
This
But then these tests would probably not going to work,
yeah.
because whatever the effect of entanglement is, it's not going to show up
So what
in
we,
those experiments.
what we are saying is speciality this, these effects have never been observed. So he's already discredited ER equals EPR. So we are using existing data.
I think we can make probably a better conclusion that the model that we have chosen to represent wormholes, and that thing is probably not a
So-
valid model.
So that's why I'm saying that ER might not be EPR. Might not be.
The objection might be something different. There's a model that the assumption you have chosen.
Yes.
One of them might
Yes.
might be modified
Exactly.
in such a way that ER equals EPR is still rescued.
Yes. So that's what I'm saying. If our assumptions are true, then the high precision data on hydrogen suggests that ER might not be.
Because that model, then we'll have to do something for uncharged entangled particles.
Yes.
Because we'll have to think of something else that's leaking out,
Yes.
because there's
Yes.
no electric field. So
Yes.
it means just a model that is based on electric field leaking out is, first of all, not a universal model, and
Yeah.
at least it doesn't give results in this way. Very, I think this is very interesting, and
Yeah. I agree with you. Yeah.
I think their point might be that the original proposal has no assumptions or anything concrete at all.
Mhm.
This is
So-
a proposal to
Yeah.
So just to
What's fundamental about ER equals EPR?
No, exactly.
yeah, exactly.
So-
So just to add to Dr. Moses' point, so there have been papers on this, that this proposal doesn't work. But all of those papers were put aside by the progenitors of this model that they use classical wormholes. The new thing that we introduced was that we're working with quantum wormholes. Therefore, we could allow things like leaking of the electric fields into the wormholes. That won't happen for classical wormholes, as I said, because a continuous topology change would not allow electric field lines to break. And these effects should not be observed for classical wormholes. So we are working with quantum wormholes. That's the difference from the earlier work in this direction. And
I think that it might be because what I have gathered from this work, not your, but the work that works on entanglement and gravity's link, is that for black hole, we can say it's a property of a black hole that the entanglement is linked to sort of the surface area of what of the horizon and these things. But in general, probably that might not be true.
yeah, so the conjecture by Marley-Sen, that's a conclusion that's generally accepted. But Marley-Sen and Susskind took an additional step. They said that it's true for all particles, not just black holes, it's true for any pair of particles. And that's what we are tackling.
At least you can say it's cycling not true for two charged particles.
Yes, yeah. Maybe on a macroscopic level, in some thermodynamic sense, yes. Not for in a microscopic sense.
What about two charged black holes then?
That's
also it's a bit Irfan, have you done with your presentation?
I was just so I was just adding.
So he wasn't asking, he was telling you.
No, because I have a question.
Yeah, sure.
Short question.
Just one comment. So the thing that you mentioned about experiments that have been done on entangled, on differentiating between spectra of entangled and unentangled system, this was exactly the point that my supervisor raised, that this proposal seems to be saying that looking at a Hamiltonian, which involves, say, more than one system, you cannot tell its spectrum, which is just a mathematical question. You look at a Hamiltonian, you can calculate its spectrum. What does this have to do with knowing the entanglement between the components of that Hamiltonian? I mean, no one has ever asked the question that given the Hamiltonian of two interacting electrons, you have to know whether they're entangled or not to give the spectrum. This was the point he raised, which I couldn't answer, and which should turn the direction of this project from.
Yeah, but there's, very big assumption in writing the Hamiltonian is that the entanglement is being linked to an additional area through which something is leaking out. So that assumption is what is causing all the predictions.
Yes. So we are assuming that the system would ultimately turn into a configuration where the liquid is leaking. Yeah, it is an assumption. Yeah, I guess I'm more or less looking.
So if I do not know if I fully understand, because I'm very basic. With me, I don't even know what a wormhole is. How is it defined in space time? But if you have a system which is entangled versus a system which is unentangled, the spectrums can be very different. For example, if I look at the case of hydrogen molecules, then you take into account the symmetrization postulate and the Pauli exclusion principle, the two spin isomers,
Yes.
the ortho and the para version. The para version is perfectly purely spin entangled because hydrogen has been cooled down to a very low temperature. So overall spins are fermion. So overall the wave function has to be antisymmetric.
Yes.
The spins turn out to be in the singlet state. It's an entangled state. So if you look at the nuclear spectrum, the nuclear magnetic resonance spectrum, it's of a particular form. The other spin isomer of hydrogen, the ortho form, is an equal mixture of two unentangled, two separable, and one entangled state with a different degree of entanglement. It's a mixture of triplets, and the spectrum comes out to be totally different. In fact, parahydrogen doesn't give any spectrum at all. So the two spectra are really different. So there are spectroscopic tests that vary between entangled and unentangled forms, and the spin isomerism of hydrogen or fluorine or any diatomic molecule which comprises two spin half nuclei is a testament to that.
Yes.
So what you're trying to do is you're trying to look at the existence of wormholes. That's an additional that it's special about your work.
Yes.
Whether these wormholes exist or not.
Yes. So if they exist, they're gonna have some effects, right? So we're looking at if those effects are there, what's the import for the spectrum? Now, the examples that you have given, they could all be explained without the existence of wormholes, right? You don't assume that there are wormholes. Right. Now, suppose that in those examples, I put in the wormholes and I include these effects. Can I calculate the same spectra that you described? If they're different from those, then certainly, and we can explain the spectra without the existence of wormholes, certainly this is something that's not true.
Right. So if you're not looking at the electric field, and so your derivation of those effects stemmed from using electric fields and Gauss's law.
Yes.
And the areas of wormholes.
Yes.
So what if you have some other degree of freedom? I mean, how does a wormhole relate to all of this? I still do not understand this very basic thing.
So let's not use the word wormhole. Let's say some extra handle on space on your space. You have let's work in a low dimensional space for simplicity. Let's work on a piece of paper. I'm introducing some extra piece that my things could flow into, could leak into. That's causing this issue.
Fundamentally, you're trying to test ER equals EPR, right? So
Yes.
the wormhole comes in from the ER part.
From here.
Presumably, there could be a spin-spin interaction taking place through the wormhole that otherwise may not be possible.
Yes, yes. So, I mean,
Not just with
the,
electric.
yes, exactly.
Okay, so online audience, I've already written in the chat. If you have a question, please raise your hand. People sitting here, Hamas, go ahead.
दो questions हैं. एक तो has anyone tried to calculate the spatial entanglement?
Yes, I have.
You have?
दूसरा सवाल आपको
So
पूछने
does
की
that-
इजाजत अभी नहीं मिली।
मतलब ये भी तो does that counteract it or does it increment it?
It increases because so you have two Hilbert spaces. Those are the spin Hilbert spaces, and you have the spatial Hilbert space. So it only increases the entanglement.
So the situation would get worse actually.
Yes, exactly.
Destructive interference.
यार देखो जब आपने कह दिया ना 13.6 से 9.5 हो गया,
Yeah.
इसके बाद कुछ और कहने की जरूरत नहीं पड़ती, इसके बाद you just put a full stop there and that
Yeah,
would be
yeah.
the end of it.
Yes.
But anyway,
Uh,
after that point you're just beating a dead horse.
Yeah.
Third question ये है कि
Alright.
if we do say ER is equal to EPR, then I don't know, maybe naive, but like फिर Bell's inequality वगैरह, locality, how do things become local now?
ER equals EPR. What?
Let's say पता नहीं मेरे जहन में
Yeah,
He's
I
probably
understand.
linking
Yeah.
the motivation कि उनको क्या तकलीफ हुई थी जब इन्हें introduce किया कि ये conjecture ER equals
So
EPR.
This actually came from the idea that you have. It's from the ADS-CFT idea of having of relating the maximal extension of a short shell black hole with anti-de Sitter asymptotic regions to entanglement between the conformal field theories on those dimensions. ये उसके साथ रिलेटेड है कि वो जो आप दो कॉपीज आप कंसीडर करते हैं उसकी कंफर्म फिल्ड थ्योरीज के अगर उनके बीच में एंटेंगलमेंट हो तो उसकी जो स्टेट है उसकी खैर उसका पार्शियल ट्रेस वो एक थर्मल स्टेट आती है एंड दैट स्टेट इज टेकन टू बी द स्टेट ऑफ प्रेजेंटिंग द शॉर्ट ब्लैक होल विद एन एंटी de Sitter स्पेस. वहां से आइडिया शुरू हुआ था कि ये यहाँ पे हमारे पास ये वाले जो दो ब्लैक होल्स हैं इनके बीच में एक वर्म होल होता है, ठीक है. तो ये एक माइक्रोस्कोपिक लेवल पे आइडिया एंड दिस इज जनरली एक्सेप्टेड क्योंकि ये एक थर्मोडायनामिक वर्जन है. हमने इसको देखा नहीं, हमारे पास इसको रूल आउट करने का कोई तरीका नहीं, कहते हैं और थ्योरी से यही चीज सामने आ जाए, हम कहते हैं ओके ये ट्रू होगा. सो दीस पीपल टुक अनदर स्टेप. इन्होंने कहा कि ये हर लेवल पे अप्लाई होता है. इट्स एग्जैक्टली जैसे मेरी एक असम्पशन है कि जो ब्लैक होल एरिया वाला वो फॉर्मूला है, एरिया और एंट्रोपी वाला फॉर्मूला, आई एम applying that on a microscopic level as well. ये उस तरह की assumption है कि ये सब the problem is the original ER equals EPR जो paper है, it's a 50-page paper and all it talks it's very verbose. All it says is the same thing again and again without any calculations. It's just a proposal. It's a very radical proposal. They also agree, the authors of the paper, but this is just a proposal that it applies at all levels. That entanglement is, in fact, Leonard Susskind has gone one step further. He says that it's not ER equals EPR, it's GR equals QM. This geometry is entangled. Proposal, it's just a proposal.
I think मेरा सवाल ज़्यादा ये है कि what happened to the status of Bell's inequality then? Does that change? Am I just thinking?
Local realism basically implications है, in other words.
I've just read some conjectures.
So why would you think about that? He's already saying ER is not equal to EPR.
उसके ऊपर मैंने कोई rigorous mathematical काम नहीं देखा. I've just seen उसकी बात करने के some information gets transferred through the wormhole. उसकी बात करने की कोशिश कर रहा.
If that's possible, तो फिर that's.
मैंने सिर्फ उसके बारे में wild conjectures देखे हैं. Never seen a rigorous mathematical work. So Leonard Susskind ये कहता है कि अगर wave function है ना, you write a single particle wave function, not two particles. Whenever you talk about entanglement, you're talking about two particles. You talk एक single wave function, उसकी one peak यहाँ पे, one peak उधर, दोनों एक दूसरे की तरफ move कर रही है. वो कहता है कि इसकी जो degrees of freedom यहाँ पे है ना, we can entangle them with those degrees of freedom through a wormhole. और वो फिर वाइल्ड मैंने देखा इस तरह की बातें उसी पेपर में मैंने पढ़ा कि किसी तरह से इंफॉर्मेशन ट्रांसफर हो जाती है जिससे वो कोलैप्स वगैरह होता है फंक्शन, बट आई हैव नेवर सीन अ रिग्रेस मैथमेटिकल, सो आई वोंट लाइक टू कमेंट ऑन।
इरफान, ये अगर ये वर्म होल हो, इस तरह की चीज हो, तो परमिटिविटी नहीं बदलेगी, रिलेटिव परमिटिविटी? अभी आप सारी वैक्यूम परमिटिविटी आप इस्तेमाल कर रहे हैं और सारी बुनियाद उसी चीज पर है ना आपके जो।
यस 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 यस,
उसका इफेक्ट कहाँ पे है इस कैलकुलेशन में?
आई थिंक
क्या पता वो काउंटर एक्ट कर दे इस चीज को, जो आप 4-5 इलेक्ट्रॉन वोल्ट का जो डिफरेंस आ रहा है उसकी।
सर मेरे ख्याल से उस,
क्योंकि वो परमिटिविटी का क्या ओरिजिन यही है ना, चार्जेस की रीडिस्ट्रीब्यूशन है, पोलराइजेशन है वैक्यूम की।
यस 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 सर, आई थिंक आई लाइक टू view that question as a rereading of the equation जो यहाँ पे मैंने की। आप उसको चार्ज के इफेक्ट में देख लें या उस फैक्टर को उधर डाल दें, अल्टीमेटली तो हम ये देख रहे हैं कि इलेक्ट्रिक फील्ड एक ज्योमेट्री में लूज हो रही है। ज्योमेट्री वो सबकी परमिटिविटी है कि आप उसको ऑन एवरेज ऐसे व्यू कर लें कि वो फैक्टर किस तरह से आपने परमिटिविटी में इंक्लूड किया हुआ है। I'd like to do that as that.
Okay, so we have a question over here. The person cannot speak because it's a microphone problem. The question says, so how does entanglement connect space-time, like you mentioned in the beginning of the talk? Doesn't it violate the monogamy of entanglement?
I don't see how it violates the monogamy of entanglement, but how it connects space-time is a paper by Ramsdonk. I think it's called Generating Space-Time from Entanglement. जो उसमें वो ये शो करता है कि जब आप दो स्पेस टाइम रीजन्स के बीच में एंटेंगलमेंट कम करना शुरू कर देते हैं तो उनके बीच का प्रॉपर डिस्टेंस बढ़ना शुरू हो जाता है। और वहाँ पे जो स्पेस टाइम कंसिडर किया गया वो एक स्फेरिकल स्पेस टाइम कंसिडर किया गया, और वो ये भी उसमें फिर ये शो करते हैं कि वो जो दो स्पेस टाइम रीजन्स हैं वो मुख्तलिफ ऑपोजिट हेमिस्फीयर्स में लिए गए, तो उनके बीच का प्रॉपर डिस्टेंस इंक्रीज होने लग जाता है और उनके बीच की जो वो मिनिमल सरफेस एक बनती है वो उसका एरिया डिक्रीज होना शुरू हो जाता है। सो दैट्स इंटरप्रेटेड as an introduction of disconnectivities in space time through decreasing entanglement. जब आप entanglement increase करते हैं वो proper distance कम होता है और एरिया बढ़ जाता है, so that's viewed as a connectivity. Very good question. ये उसको precise करने की कोशिश की जा रही है, वो जो connectivity का हमने notion किया था. Yes, this is how it's viewed in the literature.
Any other question?
Irfan, यहाँ you have one free parameter alpha.
Yes.
Suppose we fix it somehow from some theory
Yes.
of whatever.
Yes, sure.
Achha, the hydrogen atom itself also has a free parameter which appears in the spectrum. जो उसकी self-adjoint extension बताता है.
Okay.
Hydrogen atom की.
Yes, yes, yes.
Can't I just use that to fix the spectrum? ऐसे आपका alpha कोई ले लें from some theoretical calculation has some fixed value. I just match जैसे हम अभी करते हैं. We don't know what that value of that self-adjoint extension parameter is.
Yes.
We look at the experimental results and कहते हैं ये है.
Yes.
अब आपके alpha की value अगर ये है, can I do the same thing with a different value for that parameter?
Sir, मेरे ख्याल से आप so you're trying to impose constraints on alpha from experimental data?
Kind of. I'm saying alpha आ गया किसी theory से. अभी तो आपने different values दी हुई है ना.
से आ गया मेरे पास.
Suppose you have a fixed value of alpha.
Yes.
Now again we look at the spectrum, the energy spectrum. This energy spectrum in the hydrogen atom, there's another free parameter which is the self-adjoint extension.
Yes, yes.
So can't I just?
जैसे इन्होंने hyperfine का जिक्र किया है कि उसके अंदर एक तीसरा split आना चाहिए.
I don't know उसमें आता है कि नहीं वो the same parameter.
Even if it comes to you'll have like it's splitting that structure, so it's not like a common thing.
Is it not? हमने वो जो self adjoint वाला parameter है, we have chosen a self adjoint extension, right? जब हम spectrum calculate करते हैं.
Yes, yes.
Isn't that chosen from experimental data?
Yes.
हाँ तो वो ये कह रहे हैं ना कि भाई आपका इफेक्ट डाल दिया है, मतलब सवाल उनका जो अब वो तेरे जो 9.1 से आगे जाने की जरूरत है, तो कहने उसकी वैल्यू मैच करनी है ना, तो वैल्यू ऐसे मैच कर लेंगे वो वर्महोल डाल के वो आ जाता है कि वो सही आ जाएगा, बाकी but it's not going to fix the hyperfine thing because it's like a free split, it's a split free.
And also so उससे मेरे ख्याल से ये, so if suppose that alpha doesn't come from a theory, I think I've done this calculation. उसमें ये होता है कि जो आपका अल्फा अगर आता है ना, क्योंकि एक पैरामीटर को आपने फिक्स किया हुआ है एक्सपेरिमेंट में, जैसे सल्फेट जॉइंट एक्सटेंशन, आप अगर अल्फा कैलकुलेट करते हैं, इट टर्न्स आउट टू बी लाइक 10 to the 10, 10 to the 20.
अच्छा, that would match these energies with the
जी जी
spectrum.
यस, अगर आपको स्पेक्ट्रम की एनर्जीज मैच करें,
अच्छा,
एंड दैट वो हम फिर अनफिजिकल उसको इसलिए व्यू करते हैं
Right.
क्योंकि हमने ये कहा था कि वर्म होल्स डिग्रीज ऑफ फ्रीडम को ज्वाइन करेंगे। If alpha is 10 to the 20, they are not really connecting
Right.
degrees of freedom.
Right.
So we are moving away from the ER equals EPR auxiliary. So
No matter how you say, yeah, that's not equal to.
yeah.
Okay, Ji, any other questions?
वो relaxation mechanism.
I am the one.
Yes, Irfan साहब को पूछ रहे हैं।
I am the one who gets to say किसको सवाल पूछने का हक है। मैंने वो पढ़ लिया है और मैं उस सवाल को नहीं दोहरा रहा हूँ, ठीक है? So I'm in charge of the session. आपने कोई सवाल पूछने, आप पूछना चाह रहे रिलैक्सेशन में, आपसे रहदगी में बात हो सकती है। See, any other questions? If not, then let's thank the speaker. And I hope that there's tea, but I'm not sure. All right, G, thank you, online audience. This is going to be a regular feature. We won't have a talk next week because it wasn't planned. क्योंकि सबका ये ख्याल था कि अगला फ्राइडे जो है वो ऑफ होगा बिकॉज ऑफ 12 रबीउल अव्वल, लेकिन पाकिस्तान में बादल छा गए तो चांद किसी को नजर नहीं आया, which means कि Friday is not a holiday, but we're still not going to be here, but we will be here for the remainder of the semester, so please keep tuned. Bye-bye.